We've done partial fractions with linear non-repeated factors. Let's look at linear repeated factors. So first of all, we know we're going to do partial fractions because the denominator factors, and it's obvious in this case because it was given to us already factored. So first of all, the setup on something like this, when it's repeated, your setup is going to be that factor on this side. You're going to have that factor to every degree up to the degree that you have in the expression. So it's x plus 1 squared. So one of them is going to be x plus 1 to the first. The next one, x plus 1 squared. And you're going to keep going until you reach the degree you have over here. Thankfully, we're only second degree, so we only have two of them. But if this had been to the fifth, you'd have a first degree, second degree, third degree, fourth degree, fifth degree. Each one of those with a constant on top, A, B, C, D, E, however many you need to get up to the degree that you have in the integral. OK, so again, after this, everything's the same. Really what changes with the type of factors is this. How do you set it up? And that's really a matter of how the algebra works. And so we've got it set up. Now we do everything the same. Clear both sides. Again, this is always, the left-hand side denominator is always the common denominator. So multiplying by x plus 1 squared on both sides. Over here, that's going to cancel it off. Over here, when I distribute it through to the first one of my x plus 1's cancel, but I'd still have an x plus 1. When I multiply x plus 1 squared on this one, it cancels off completely. And we have something like that. Now think about if you wanted to use the shortcut at this point. You'd plug in a -1 for x to get rid of a, and you could solve for b. So the shortcut would work. But there's nothing you could plug in that's going to get rid of b because there's nothing on b, right? So this is the problem. So you could use a combination. You could use a little bit of the shortcut, a little bit of matching coefficients. But this is such a simple problem in that there's only two unknowns. I'm just going to do it all by matching coefficients. If you have a lot of unknowns, it's nice to pick off as many as you can by the shortcut to lessen the work, but there's not much here. So distributing, the coefficient on x is just a. Then we have a plus b for our constant. Now we match our coefficients. Remember, this is an identity. Left and right-hand side should be equal for all x. So the only way that's true is if they're the same polynomial. So the coefficient on x should be the same on both sides. So a has to be 2. And the constant should be the same on both sides. So a plus b has to be 5. Which means a is 2. Nothing to do there. So plugging in here, 2 plus b is 5. B is 3. OK, so returning to our problem, this was just to break it up. So what do we have? A, make sure you put these in the right spot. You know, there's really nothing special about what you want to name these. That could have been A and that could have been B. But whatever you get, make sure you put them back in the right place. So A is 2, and A was what I called the number on top of x plus 1. And b was 3, which was what I called the number on top of x plus 1 squared. Now, we know how to integrate that. Again, both of these are technically u-subs, but they're linear ones. And that linear shortcut that I talked about at the beginning of the semester just makes these problems so much easier. All you have to do is divide by coefficient on x, which is 1, so really don't have to do anything extra there. Now be careful, it's tempting. So many, since these linear ones are always log, it's tempting to call that natural log. But now that's really like something squared, so it's power rule. So it's something to the -2. Raise that by 1, it's now to the -1. Divide by -1. So you have minus 3 over x plus 1. Okay, so for linear repeated factors, you're going to have that factor to every degree up to whatever it is. For linear non-repeated, you just have the factor. You could have a combination of both. If this had been multiplied by, say, an x minus 2, then you would have another term here with just c over x minus 2. So you might have a mixture of some linear repeated and some linear non-repeated. You just put those two rules together into one big expression there.